Okay, so we're very happy to have Aleix, Gimenez-Grau from IHES. Excuse for my pronunciation. And Aleix is visiting us, and he will tell us about the Witten diagram Bootstrap for holographic defects.
Yeah. Thanks for the invitation. It's been a very nice week. And yeah, I'm going to be talking about some work in progress, which is continuation of previous work that we did with Julien Barrat. She's a PhD student in Humboldt University and Pedro Liendo in the in campus. So maybe so before I start describing the setup of the talk, let me motivate it a little bit, like with an analogy from scattering amplitudes. So in principle, we all learned in QFT course that, I don't know, when you have, let's say, Young's theory and you want to compute some amplitude of gluons, in principle, you just go ahead, compute all your Feynman diagrams and get the answer. So in principle, this should be straightforward. But in practice, even when you look at some tree-level process, let's say some 2 gluons to 8 gluons, you would end up seeing that there's I don't know, 1 million diagrams, and you have to compute them all. You have to be very careful with the polarizations, all the vertices, and eventually at the end you're going to get some result that is extremely simple. So that motivated people to look for better formulations where you're actually avoiding off-shell quantities like Lagrangians, Feynman diagrams, etc. And instead you look directly at off-shell quantities such as the final scattering amplitudes. So in particular, they found that some of these scattering amplitudes, they show remarkable simplicity. So there's this famous MHB amplitude that can be written for arbitrary endpoint gluon amplitudes, and you can write it in some very simple form, but it's important that you use the appropriate variables. So in this context, the appropriate variables are the so-called spin or helicity. And also the nice thing about working with one-shell quantities is that sometimes people have uncovered hidden structures. So there's sometimes symmetries like dual conformal symmetry that wouldn't be manifest from the Lagrangian, but it turns out that it's there. And similarly, there's other structures like color kinematics duality, etc., that have been uncovered in recent years. So today what I'm going to do is I'm going to try to do something similar, but in the context of ADS-CFT correspondence. So in the context of ADS-CFT correspondence, the analog of a scattering amplitude, it would be let's say you start with some string theory, so then you would have scattering of closed strings. But then since we are working ADS-CFT, we are looking at some low energy description. So instead of strings, we can imagine some supergravity fields. And since we work in ADS, what we have to imagine is having some field in ADS and then bringing this field far away, close to the boundary of ADS. So this is the analog of creating some in state and some out state. And that's what I'm representing here schematically with this diagram. So that's a so-called Witten diagram, and this is supposed to capture a correlation function in the dual CFT. Again, in principle, you can use some off-shell methods to compute these Witten diagrams. So in particular, you can have an action, a Lagrangian, which is off-shell, and then you can use all the vertices to compute the Witten diagrams, and at the end you get this CFT correlator. But that tends to be very hard, again, because there's lots of diagrams and calculations become cumbersome. So a few years ago, there was a very nice paper by Leonardo and Shinan, where they managed to apply this on-shell philosophy. So the idea was to actually look at the final quantity, which is a CFT correlator, and by using a nice language, which in this case is something called Mellin space, that I'm going to describe briefly at the end. By using this type of language, they managed to find closed formula solutions for the 4-point functions of certain operators in a holographic set. And again, the philosophy was similar to what you have in scattering amplitude. So you know that this amplitude has to have certain poles in certain locations, so they managed to make some type of ansatz and then demand supersymmetry and fix the full zone. And similar to what I was saying before, this actually turned out to uncover more structure than was known before. So in particular, 1 year or a couple of years later, that this formula appeared in a nice paper by Simon and Ancoy. They managed to explain the simplicity of this formula coming as from some 10-dimensional hidden conformal symmetry. I'm going to explain later at the end, more or less how this study goes. And also, like, since then, there's been a lot of progress. Now people can compute 5-point functions, or like Ethan, for instance, has nice papers on how to compute like string corrections to these correlators. So this would be like going to one loop in some sense. In the analogy with string, with the scattering amplitudes. So today what I'm going to do is another generalization of this setup, and what I'm going to do is consider the presence of branes in ADS. So in particular, we know that there's the duality between string theory and a CFT at the boundary. So in particular, like all these extended objects that we know that are there in string theory, like I don't know, the branes or like strings or whatever, all these they should have an analog in the CFT. So in particular, the type of questions that we would like to answer is like, okay, can we compute a correlator where there's like some brane in ADS, and then there's like some closed string that scatters in the brane, and then it emits like another closed string. So that's the type of process that I have in mind. But instead of working like this would be like some flat space string description, I'm gonna be imagining that this happens in ADS, and it's like in low energy. So instead of a string, this is gonna be like some supergravity. Okay. And some of the questions that we would like to answer is whether this type of process, whether it's fixed by symmetry and consistency conditions, whether you need to know like in detail what type of brane you have, what type of operators you have, like how much of it is prefixed, is there maybe some hidden structure behind? And so today what I'm going to do is I'm going to follow up on some previous papers where we managed to compute some of these correlators and present a more systematic procedure. And it's going to allow us to answer some of these questions. So just to give like a brief outline of the talk, for concreteness, I'm going to focus on the case of n equals 4 super young means, which is dual to type 2 supergravity. And this brane that I was describing, in my case, it's going to be a fundamental string. So there's ADS 5, and there's some fundamental string that lives in some ADS inside ADS. And many times I'm going to just call this brane a defect, because it's very common in the CFT literature to call these things. And like a rough outline of what's the approach that we are going to follow, the idea is going to be to try to make an ansatz for the final result. So we want to compute this type of correlator with closed strings and a brane. So we make an ansatz for how the final result could look like. Then we are going to compute the building blocks in this ansatz. And then we are going to fix these ansatz by demanding that all these building blocks satisfy supersymmetry conditions. So, and at the end, there's always some overall normalization that you also have to fix. You can fix comparing to localization.
So you're specializing in line defect because you're
exactly. So from the CFT perspective, like this thing is line defect because this ADS2 it intersects the boundary. But then like this is really like a surface in ADS.
This is a string, which means a two-dimensional surface.
Yes.
So what does it mean, string in ADS2?
No, so the string extends, yeah, like maybe it's in is not proper.
So the surface. I mean,
the surface forms an ADS2 inside ADS. Now I'm going to describe the setup in a bit more detail.
You mean, sorry, do you mean Euclidean or Minkowski?
Yeah, Euclidean. Okay. So as I was saying, like by this procedure, we can actually manage to compute many correlators. But like coming back to the analogy with the scattering amplitudes, something that was very nice is that when you actually express the result in the right variables, in that case it was like spin or helicity, the result turned out to be very simple. So here there's something very similar. What we have to do is we have to do a Mellin transform of the result. And it turns out that something that looks very complicated in Mellin space is going to look very simple. And we are actually going to be able to find a closed formula for the final cost. Okay. So if there are no more questions, maybe I can move on to the first part of the talk. So the first part is going to be understanding how to make these ansatz. So what are the fluctuations that contribute to the correlator? And then I'll quickly compute the building blocks and fix the result. So let's start to explain in more detail what we are studying here. We are gonna be focusing on some local operators, which are perhaps the simplest local operators in any post-for supergiant fields, which are chiral-primary operators. So they are just like a product of p copies of a fundamental field, and then you take the symmetric traceless combination, and then you take a trace for each invariance. And now it's well known that these CFT operators, they are dual to certain Kaluza-Klein modes in ADS5. And there's a relation between the mass of these Kaluza-Klein modes and the dimension of the chiral-primary operators in the post-for. Now, as I was saying, my extended object is going to be a Wilson loop in the CFT perspective, and it's not it's not the standard Wilson loop, but instead it's a Wilson loop coupled to one of the scalars, and that's done in such a way that this combination preserves half of the supersymmetries of any post-for superlative. And following the IHES dictionary, this should be dual to some fundamental string, and the action of the fundamental string is just like the pullback of the bulk metric to some ADS2. Then finally, the process I want to study is what I was saying, like some scattering of a local operator out of some new branes. So then, like you need to group two local operators, the extended operator, and then in supergravity, what you are going to have is like diagrams like this. I'm going to explain them a bit more, but like this is the local operator that propagates like an ADS5, and then this would be the extended object that extends inside the ADS5. I'm going to explain the notation. But now, first, what I would like to explain is what type of fields can be exchanged in ADS5. So this is a question that is well understood it's been understood for many years. So the idea is that you start with type 2D supergravity, and you compactify it in ADS5 times S5. So by compactifying, it means that you expand all the fields in the supergravity in terms of some spherical harmonics that live in the S5. Then you get like some complicated mixing problems, but then you can find like what are the fluctuations that have well-defined mass. And these fluctuations, they turn out to form multiplets under the symmetry group that's preserved by this. So the symmetry group is PSU 2,2/4. It's the symmetry group of any post-for superlimit. And then like the operators, as you can see, they form multiplets under this. So these three operators here, they are some of the operators in a certain number. And then what you should imagine is that for each of these operators, you can always prepare like you can put some operator at the boundary, and then this thing can fluctuate in the bulk, and then in the bulk it can interact in some non-trivial way, and that's what's going to make like some process happen. And yes, I was saying like you can make them propagate in the bulk, and you can also make them interact in the bulk. Like here, like in principle, this action contains many different vertices with some coefficients in front that are well known. But it's quite complicated to actually like figure out exactly like what vertices are there. And similarly, like if you take the string action, as I was saying, this is the bulk metric that you pull it back to the string wallsheet. So then, if you allow the bulk metric to fluctuate, that corresponds to those fluctuations over there. So then, like expanding this thing to linear order, you can obtain how all these operators couple to the string wallsheet. So essentially, this thing corresponds to some 3-point vertex, and then this thing corresponds to the string wallsheet absorbing an order. I'm going to explain this graphically again.
Sorry, the fields on ADS2 can be different from there could be additional fields on ADS2 which do not exist on ADS.
Yeah, and
those actions.
And I'm going to describe them in the next slide. Yeah, but you are absolutely fine. So this only contains the bulk fields, so the things that we did in ADS2, and how they couple to the ADS2. But as Himanshu was saying, there are more fields. So here the picture that you should have in mind is that you can go to the boundary of the ADS2, and then you can put there like some local operator, and then the thing can propagate inside the ADS2. So again, this type of operators, from the supergravity point of view, you should imagine that they correspond to fluctuations in the geometry of this string motion. So in particular, this string motion is at a certain position in the ADS5, but it can move like in the transverse direction. So these are one of the fluctuations you can have, and I'm calling them xi. And then this string motion also has a certain direction in the auxiliary S5. So then you can also have fluctuations in this S5. This is what I'm calling y. And again, like you can expand the string action, and then like to quadratic order you find these terms. So remembering the relation between the mass and the dimension, you can see that there's what people usually call a displacement operator, which is an operator with dimension 2 and some spin 1. So the spin corresponds to the fact that there's like 3 transverse directions in which like this string motion can move. And similarly, there's a field operator that depends on this the index. And in this case, like it's an index in 5 dimensions, which corresponds to like so there's an S5, so it corresponds to the coordinate index.
That's why there's no y squared. Because there's no.
No, there could be y squared. The point is that if you want, like from the CFT point of view, you know that this guy has to have dimension 1, so then the mass has to be 0. But presumably it's not completely obvious that the mass. Like for instance, if this instead of being like a line defect, if it was a surface defect, then there would be a mass. No, it would always be mass. Sorry, yeah, because it's gonna be it's gonna be minus marginal. 2. Yeah, it's gonna be dimension 2. Yeah. So anyways, so that's the quadratic part of the action. But there are also like interaction vertices. So in particular, you can have like this S was a bulk operator, let's say, and it can couple to these defect fluctuations, these x and y. So just to summarize what I've said, we have some operators S, T, and phi that live in ADS5, and we have some fluctuations x and y that live in ADS2, and they interact in that. So with these vertices, we can go ahead and start writing diagrams. So the first 2 diagrams, they are kind of trivial. So the first one appears at order 1, and we have no interaction. So you just have like one single phase operator propagating and being absorbed by another single phase operator. There's no interaction. It's just like some kind of, it's like a very simple. And here, like you basically have like one local operator being absorbed by the wall-sheet and another operator being absorbed by the wall-sheet. But again, there's no interaction in the path. So these 2 things, they cannot factorize, so you can subtract from the full correlator. And the leading non-trivial correction to the correlator, like maybe you could even call it some kind of the connected part of the correlator, contains these diagrams. So in the first one, I'm using one of these 3-point vertices in the bulk. And then I can exchange either S, phi, and T, and then each of them can be absorbed by the string motion. Then in the second type of diagram, the idea is that like the local operator is going to excite some fluctuation in the string wall-sheet, and then like this is going to eventually emit like some closed string. Okay, so these are the diagrams that I would like to compute, and instead of going to the action and then figuring out all these vertices and trying to write down like all the diagrams very carefully and try to get the final result. Instead, I'm just going to make an ansatz and try to fix like what's the correct combination of these diagrams that is physical, that can satisfy supersymmetry. So if there's no questions, I would go ahead and explain like first how to compute each of the diagrams, and then I would explain like how to fix the relative coefficients. But if not, maybe here it's a good moment to start. To ask questions if you have like some doubt about stuff.
So S, phi, and T are in the same multiplet?
Yes. So here, this multiplet contains many more operators. Like maybe you
But the ones
probably know,
relevant
but
for
then
this
like most of them, they do not couple to the string walls.
Yes.
So that's why here there's only a slide. But it's true that like they are all from this prime multiplet and the higher versions.
putting asymptotic states at all on the ADS too?
No, I am not, but it's because I'm considering this type of correlator. I could consider, for instance, a correlator where this, instead of being an operator, it would be like, from the CFT perspective, you have to imagine like a line defect. Now what I'm doing is I'm putting some operator outside and some operator outside. But I could consider, like from the CFT point of view, I could consider some correlators. And that would correspond precisely to sending some asymptotic states from here.
Sorry, how in x times s and y times s, how are the indices separated?
Yeah, like you can see it here. I wrote it. Sorry, here I wrote it in a bit more detail. For x, it goes like this. So here you are taking covariant derivatives only like in the directions orthogonal to the ADS5. And here I didn't write the indices, but because I'm being very schematic about the asymmetry index. But this y, it would contract with some spherical harmonic that lives in DS5. So this, yeah, I can write it later if you want. Any other question? Okay, if not, I'll go ahead and explain like how to compute the building blocks. I'll try. This is maybe the most boring part, so I'll try to do it fast. But so before I start, I introduce some notation. So for points that live in ADS5, I'm going to use Z. For points at the boundary of, for points at ADS2, Z hat, and then for points at the boundary. So I think this is kind of standard notation. And then in order to construct these Witten diagrams, one needs to use propagators, like same as for Feynman diagrams, right? So you have the bar-to-bar propagator, which is just a solution of the equations of motion in the bulk for a massive pattern. Right? So you write down the equation, you solve it, it's complete. And then you have the bulk-to-boundary propagator, which is just taking some limit of the bulk-to-bulk propagator where you send them bulk to bulk. And then
identify U.
Yeah, U is some combination of Z1 and again some cross ratio. I can write it. And then because of the symmetries of the problem, all these Witten diagrams, they are going to preserve some subgroup of the conformal group. So the idea is that because there's this symmetry that is preserved, then you can always like constrain the final answer using conformal symmetry. So in particular, you can strip out like some dimension 2 factor, and the result can only depend on some conformal ratios. So in this context, I'm just calling them R and W. It doesn't really matter. Like I'm not going to use these formulas in the rest of the slides, but just for you to see that it's some very explicit combination of the coordinates of x1 and x2. And then let's compute the simplest of all the diagrams that we need. So the simplest one is the contact diagram, and in the context of 4-point scattering, these things usually are called D functions. So D delta 1, delta 2, delta 3, delta 4. And these are well-known special functions. So these have been studied for a long time. In my case, these are even simpler. So I'm going to call them C. And it's just like an integral of 2 bar-to-boundary propagators, and you need to integrate over ADS2. So in particular, remember that this K is a very simple function, so then this integral you can just go ahead and compute it. Turns out to be some hypergeometric function. And in particular cases, delta 1 and delta 2 are going to be integer. So then, like when delta 1 and 2 are integer, this just reduces to some logarithms. Some logarithms and some rational functions. And now the reason why this is so important is because actually it turns out that you can use contact diagrams as building blocks for more complicated diagrams. So the first case where this happens is for bulk exchange. So for bulk exchange, you have here some 3-point vertex in the bulk. So then you need to integrate over the vertex in ADS5 and the vertex in ADS2. But the internal propagator is some complicated hypergeometric function. So in principle, this integral is hard. But there's a nice trick that we developed already like in the early days of ABS-CFT that allows you to reduce this to a sum of contact diagrams. So This can be made like very explicit, for example, for scalar exchange. And here I just write the formula for you to see that it's actually like very concrete. So if you want to have like some external operators with dimension 1 and 2, and you want to exchange something that has dimension delta, you can reduce it as a finite sum, and each of the terms is just a contact diagram. So it's like extremely explicit. For other exchanges, for instance, like for a spin to exchange, like this gets more and more complicated. So then like you cannot write it explicitly, but you can compute it in mathematics. Then similarly, there was this other diagram that we have to compute. In this case, you have again like some back-to-back propagator that is restricted to live on the IHES2. And again, in principle, this integral would be hard, and sometimes you can manage to reduce it to a sum of contact diagrams, but not always. So then, instead, there's another method that is also very efficient, which is to solve the equations of motion for this. So the idea is that you act with the equations of motion on the diagram. You can kind of imagine like the equations of motion going through the integral, then they are going to hit the bulk-to-bulk propagator, and that's going to give a delta function. So when you have a delta function, then it means that that integral just reduces to a contact diagram. Okay, so essentially the trick is you act with the equations of motion, you get the contact diagram on the right-hand side. This has a very simple form in terms of logarithms and rational functions. So then this equation you can also solve like very easy.
Sorry, which point are you applying the equations of motion at?
Yeah, I'm a bit schematic. Like here, you actually apply the equations of motion at one of the external points. But then
External points are only x1 and x2, right?
Exactly. But then by conformal symmetry, you can move the action from x1, you can move it to z1.
z1 is being integrated over, so
I know, but it's some trick. Like I can show you.
It's like the function depends on like on the different x minus
yeah,
y.
that's right. Yeah.
Exactly. It's a bit like this.
Yeah.
Yes. You make it go through because it only depends on x1 initially, but then you convert it into the derivative. And again, since this is just like some rational functions and logarithms, you can easily integrate, and the result again is some rational function of r's and some logarithms.
Yeah, but I think here you act on the boundary, right? It's not D2 IDS2, right? It's D2 on the boundary.
Can you say again?
Oh.
So here, yeah.
Yeah,
So
it's
here,
not IDS2 here, it's IDS5.
no, it's ADS2 because
Same confusion.
so the point is that this propagator here,
Yes.
it lives here like inside ADS2.
Yes.
So then you really want to act with
Because
the
it's
cousin.
function dependent. Oh, okay. Okay, but it's like exposing.
No, yeah, but I can like it's a technicality, but you can actually make it like and it has to be ADS2 Laplacian because the propagator lives inside ADS2.
I think the confusion is that x1 and x2 are in the boundary of ADS.
Yeah, it's not an obvious like it's a calculation.
But what Laplacian is you applying? That's the confusion.
Yeah, the Laplacian of ADS2. Why is this confusing?
Well, because x1 doesn't have the z direction, so you're acting the derivative at x1.
X1 does not live
I
on
see.
IDS2.
X1 doesn't
Yeah, okay,
live on
maybe it's fun notation. You're absolutely right.
Yeah.
It's
It's not a
notation.
Laplace.
Yeah, so it's like like to make it more precise, this would be the Casimir of the conformal group.
Yeah.
And then that's the thing that you can make. And then this Casimir has a certain form in terms of x1, x2. Okay, so yeah, it's true. Like this notation is confusing. Yeah, thanks. Thanks.
Just a question about limits of R. So when I bring the point like x1 and x2 together, what am I doing with R?
Yeah, x1 and x2 together, it's r going to 1. And then you can also bring x2 to the boundary of to this boundary, and that corresponds to r going to 0. And yeah, it's a good question. Like this is what in CFT we call these operator products functions. So r0 is the defect of E, r1 is the log. I'm going to discuss this one for more. Any other questions? Or if not, like this was like everything I wanted to say about how to compute the diagrams. Just like to give you a favor. Like the upshot is that all the diagrams, like for the case of interest, they turn out to be just like a bunch of logarithms and some rational functions. So it's like very easy.
of some R that you will define.
I defined it, but I can show it to you again if you like it. Some easy combination of the external positions. So these are directions orthogonal to the line, and these are also used by notation. Like this vector is supposed to be the same as this.
But just geodesic distance connected to points, and then another is
Coordinates.
I don't know. I mean, this one has an easy interpretation. So this is I mean, like both of them have an easy interpretation. For me, the nicest interpretation is to think of it like this. You can go to a plane where I don't know, like you have some operator here, O1. And some operator here, O2. So then you put them in the same plane by conformal transformations. And then like the coordinates of this plane, we are C and D bar. And then you can just say that C is R double and D bar is R over W. So essentially, R is like the distance from this operator to the defect. So then you see that when R goes to 0, you are approaching the defect. When R goes to 1, you are approaching this operator. And then W is essentially like this angle. So that's in Euclid. So they have a nice physical interpretation. Okay, good. So now we have like all the building blocks in our ansatz, and we want to fix it. So the trick to do this is to use supersymmetry. In particular, this system preserves half of the original supersymmetry in n equals for super young mills. And a very nice way to see it is using the superconformal work identities. So let me introduce some notation. For now, I've been very schematic about that symmetry and about indices. So these chiral-primary operators, they actually contain like p copies of the fundamental field phi, and each of them like has some index. So in order to implement the fact that this thing has to be symmetric and traceless, the most efficient way is to contract this on polarization that this has to be now. Okay, so the now condition implements the fact that this is traceless. And similarly, the Wilson line, as I was saying, it is coupled to some scalar. And then there's 6 of these scalars, so you can choose a direction in this 6-dimensional space. So we parameterize this direction by some angle theta that has norm law. So now in this language, what one can do is that we want to compute this correlator, so we can again factor out like some dimension full factor in some sense that depends on U's and thetas. Then after factoring this out, the correlator is going to depend on an extra cross ratio sigma, and this sigma, like the correlator has to be polynomial. So it's just going to be a polynomial, like it's going to have a term. It goes like 1, sigma, sigma squared, sigma 3, so on. And sigma is just like some ratio of these contractions of U's. Okay, so this is pretty standard in supersymmetric literature. And the reason to do this is because now that we have our correlator as a function of 3 variables, what you can do is you can just do like another change of coordinates, which is not too important, and then the effect of supersymmetry translates in a linear relation satisfied by this function. So remembering that this thing was polynomial in sigma, and sigma matched to alpha, then this is going to give you relations. Like this polynomial is going to have like functions that are all related to each other by some linear differentiation. And this turned out to be extremely powerful. So because it's a linear differential equation, it turns out that many of these like independent components are really not independent. And then as I was saying, like since we are doing this type of bootstrap where we make an ansatz and then we apply the word identity to fix the relative coefficients, there's no way to fix the overall normalization. So to fix the overall normalization, we are going to use supersymmetric localization. Again, there's many things one could do, but maybe the simplest is to consider some topological sector where you have like some sphere, And then you put your Wilson line like in a circle, in a gray circle of the sphere, and then you put your operator anywhere, like inside the S2. And then this turns out to be like what's called topological, so it means that correlators in these configurations, they don't depend on the precise positions of any of these things.
You have
In
two of
particular-
SPs, right?
What?
You have two of those SPs, so you're computing two more.
Yeah, but you're absolutely right. Like I could compute this two-point function in the topological sector, but actually since I want to determine the normalization,
One point function is enough.
then one-point function is enough, and then I can. But you're absolutely. I'm gonna make another comment related to this, like in a second. But anyways, the point is that this type of correlators, they are described by some 2D Mills correlators. This is a topological field theory, and everything you compute can be computed in terms of just like weak contractions. So you just compute all the weak contractions with the combinatorics, and you can obtain the value of this correlator. So in particular, to make it more precise, you want to compute this thing, but you can map it to some matrix model, and the action of this matrix model is just an action, so it's very easy. And as Himanshu was saying, we would in principle also compute the two-point function in the topological sector. And by the definition of this topological sector, this thing has to be a constant. So the whole reason why we don't do this is because we are interested in this dependence in R and W. Like that's really what captures the non-trivial information of this correlator. So in particular, by using operator to do expansions, like this dependence is going to give us also information on non-protected quantities. Okay, so I'm finally ready to also how am I doing?
You have 20 more minutes.
Okay, so let me show you like the simplest example of how this can be done. Like again, it's the type of thing that you wouldn't want to do by hand, but you can easily implement in mathematics. So we take down again, like as I said a million times, we make an ansatz, fix it with word identities, and fix the normalization with localization. For the simplest case, which is like having some operator of length 2, another operator of length 2, then we have 3 asymmetry channels. As I was saying, like this thing is a polynomial in sigma. And then the 3 asymmetry channels look like this. I mean, the form is not too important, but you can start to recognize like all these building blocks that I was showing you, like some logs with some rational functions. This is just like combinations of all the building blocks that we computing. And it's a precise combination that satisfies the localization. Now, we actually managed to compute this thing like some time ago using a different method. So the method is not too important, but the idea in that case was to use something called an inversion formula. And then this inversion formula kills many of these terms. And you can actually guess what, so you apply something like, you apply some kind of discontinuity, you kill many of these terms. You can guess like what the discontinuity should be. And then you, like this inversion formula reconstructs for you the rest. So now, like, even though that worked, now this other method that we have here, like it turns out to be much more efficient. So you can generate many more parameters. And they are all gonna look like this, like some complicated combinations of logs and rational functions of them. So it's very hard to see a structure.
Sorry, so how do you know that the coefficients are sigma squared, sigma, and 1? The coefficient at the top, like S2, S2. The coefficient is sigma squared and sigma and 1. Maybe you said it, I missed it.
Yeah, no, it's I can show you easy. I mean, the idea is that you have schematically like place of phi I1, phi I2, place of phi J1, phi J2. And then here you have integral of phi 6, let's say, let's pick some direction to make it complete. Then I think, probably speaking, you are going to have some symmetry structure that is delta I1, delta I1 J1, delta I2 J2. And that's going to correspond, I think, to sigma squared. But then you can also have something like delta I1 6 delta J1 6 delta, and that's going to correspond to sigma. I guess probably we can already see the pattern. There's going to be something like this: 6, 6, 6, 6. And that's going to correspond to. So that's why it's a polynomial. Like in this polynomial, we are treating these tensor structures by powers of sigma. Any other question or comment? Okay, good. So the goal of the rest of the talk is going to be to actually try to give some structure to all these correlators, because like this they don't look very manageable. But it turns out that there's like nice structure with them. But before I do that, let me give some sanity checks that these correlators satisfy. As most of you probably know, in CFT there's operator product expansion. So if you bring like two operators close to each other, you can replace them as a sum of local operators. Instead, if you bring one of the operators close to the defect, you can expand in terms of defect operators. So this allows you to take your correlator and expand it either in the bulk channel or in the defect channel. Okay, so now this correlator we have, we could expand it in these two limits. And then we can extract some coefficients, like this is here, they can be compared to localization. So the idea is that we had to use localization in the topological sector to fix the overall normalization. But it turns out that after we fix the overall normalization, many of these, like you can extract several more protected quantities and they all agree. So you require one input, but then you can check many outputs and they all work. Okay, so that's the first check. Also here, let me mention that a very important comment is that this expansion contains many operators that you wouldn't be able to compute in the topological sector. So, and that's the whole virtue of this result. You can extract things that, sorry, I was just saying that I was using here CNC lines, but now it doesn't matter. But yeah, the whole point is that many of these guys are unprotected and they are still captured by these results. The only caveat is that sometimes, like in N=4 superior mills, in other theories, there's nearly degenerate operators. And then it's a non-trivial task to figure out like unmixed combinations of CFT. But in principle, if you are able to unmix the CFT data, that could give like nice input to integrability. So in principle, this type of setup should be captured by integrability because we are in a planar limit. And then we would be giving like the leading like lambda behavior at spin coupling. And you can also easily compute these things at spin coupling, but there should be some description that interpolates in between and perhaps like some integrability people. Right? So I don't know how hard this would be to be honest.
So for the moment, the one-point function of non-PPS operator has not been extracted yet because this mixing problem has not been solved.
I don't think so.
So what do you need to solve the mixing problem? What kind of one-point function do you need? Is 2 to PP sufficient?
We have like it's something we haven't really thought. I mean, the point is that first you have to unmix in the bulk.
Yeah, so that's the one-point function I'm talking about.
And that has been, I think some of it has been done in some papers by, maybe you know them even, like by Paul Heslop and I don't remember, like Aprile and some others. They managed to unmix like part of these operators. So for them, like maybe for them, like using the fact that we know so using the fact that we can generate like lots of correlators, in principle combining the 4-point information with this, probably you can extract stuff. But I don't know, it's like tedious work and we haven't really done. Like you have to work out like all these conformal blocks carefully. It's really like it's not completely simple, so that's why we haven't done it.
So for the moment, this 1-point blocks, are they completely known?
This one?
Yeah.
I know that for the 2-2 case,
But the other ones, the G-head are known, right? So it's just the the one-dimensional conformal block.
Sorry, like the bosonic part of the blocks is known. Like, I mean, you have like series expansion.
Yeah, just combination.
But the complicated part is to figure out like all the relative coefficients
that
appear. And then that's for the 2-2 case, it's known. But I'm not completely sure if for the most general case, all possible blocks that could appear. I don't think so. I think only the ones that appear in Q2 and some others. Any other questions? Or okay, so that was one check. The other check is that, as I was saying before, like we have some ADS 5 action with some vertices that have some coefficient in front, and we have some ADS 2 action with some coefficient in front. And the point is that our bootstrap calculation, in some sense, is like predicting what all these coefficients should be. So the next sanity check you can do is you can try to do an honest calculation, and you can see that, for instance, like these black vertices that are known are exactly reproduced by this bootstrap. So you can do the calculation and see that it works. You can also extract these vertices by expanding the string action to linear order in S3 and 5. And you can also see that these vertices, they seem to agree with the bootstrap.
What about B?
And then, yeah, like as I was telling Ethan like multiple times this week, I'm still a bit confused about this type of contact vertices. So these ones I'm not entirely sure like how to work out. Like there's one particular contact vertex that I understand, but the others not. So I don't know if I'm just like missing something. Yeah, I'm missing something important or not. But I have no doubt that the full result is correct because still like this type of contact terms, they can appear like anytime you do some integration by paths, etc. You could be generating some contact terms. So it's probably just because like the calculation has not been done like carefully enough. But really like the physical information is really like in these vertices here, like A, B, and C, and these ones work. So I have no doubt that the final result is correct. But anyways, as I was saying, like before finishing, I would like to try to give like to organize like this, like all these correlators in some way that, I don't know, makes more sense, or let's say like it uncovers a bit like some of the structure different. And the idea is to go to Mellin space. So in Mellin space, instead of these R and W cross ratios, I'm gonna use something called chi-anita, or xi. I never know how to pronounce this. Whatever, xi-anita. Does anyone know? I'm always confused.
Or try.
Is what xi or xi? Yeah, xi, perfect. So basically, you just do a Mellin transform of xi and anita. So like this idea of having like xi to some power, and then here you're integrating over the imaginary axis. That's called the Mellin transform. So you do this only to the space-time cross ratios, and then you leave sigma untouched. So remember that sigma is the thing that is a polynomial to capture asymmetric cross ratios. And then the whole reason why we do this, and the whole reason why we take out like some strange looking factors of gamma, is because this Mellin transform is going to make all the contact diagrams constant, and all the exchange diagrams in the above just rational functions. So instead of having like those complicated functions of R and W, now we're going to map this to something that is just like either constant or rational. So then there's more hope to see like some pattern in the results. The only caveat is that there was this other diagram, like this defect exchange. So for this type of diagram, you do the Mellin transform, you don't get something rational. You get something that is meromorphic, it has like infinitely many poles. But sometimes it truncates and it's rational, but not that. That's the only caveat.
It's a bit like the one by amplitude. Like
Yeah.
both 4.5.
I think
It's also written like infinite sum.
It's also like so out of ADS4, I think it's in ADS4, but these things also don't truncate. Right? For focal function in ADS4, it also doesn't truncate even at 3 level.
Okay.
So you don't even need to go to it. It's just like so entirely clear why sometimes things are rational and sometimes clear. No, I think it's not really known. It's just a coincidence or there's an
Is there any interpretation of the poles of these functions?
Yes, actually there is. So that's a very good question. So you can, by doing copies, you can see that precisely when there's a pole, it corresponds to a certain operator appearing in the long expansion.
So the difference is when you have meromorphic or rational, is that you have an infinite number of things.
The difference is that, so here you're already, like, you're extracting some dependence on delta. So the difference is whether these gamma functions, whether they can cancel infinitely many of them and only leave finitely many. Sometimes you factor out the right thing that cancels everything, sometimes there's something else. So that's the best interpretation I have, like it's not very convincing. And yeah, as I was saying, so remember that what we are going to have is something that is just like a polynomial in sigma, and then each of these things, they are almost rational, except like some meromorphic terms, but they can take care of them. So,
But do you see a different way of writing the Mellin transform such that you can, remove this input codes in the defect exchange?
there's not a lot of freedom in how you can write the Mellin transform for the following reason. So,
But the faults in this defect exchange are also integer space.
see again?
The faults in the defect exchange also infinite space is integer space.
Yeah, they are also integer space. But the point is that the way you construct these things is that you say that f has to be like some integral over, I don't know. I guess usually you work in a variable space. Right, and here you put some gamma 1, 2, and then here you need to put like, you want to put distances here, right? So you want, the point is that you would make an ansatz like this, but then conformal symmetry already fixes the relative coefficient. So somehow, like, it doesn't seem like there's freedom in how you define an ansatz. Like, I mean, because if you want to have some interpretation where the poles come from doing copies, then these are the distances you have to put. Like, you need to put this distance to have a pole in the bulk copy, and you need to have this distance to have a pole in the defect. So it seems like this is kind of a unique Mellin transform. And yeah, you could play with maybe changing the constant like this gamma function, but I think you can also not play with that because eventually what you want to do is you want to make the contact diagrams constant. So I'm not sure there's any smarter choice. Okay, and besides this more technical comment, now let me present like how the correlators look like in Mellin space. So what I'm going to do is that I'm going to separate my amplitude into two parts. So first, one part that I'm going to call M bulk contains this type of diagrams, and then the part with the defect, it contains this type of diagrams. And then the contact diagrams, I need to put like some part here, some part. But there's a well-defined way to do it. And it turns out that the bulk part is extremely simple. So it's just like some finite sum of poles in delta. And then at each of the residues, then the result is just like linear inflow. Okay, and you can just use fine sequence function many times. And eventually you figure out that the formulas are just like some Bohr hammers. So that's why it's useful to be able to generate lots and lots of code. Yeah, I don't know. I mean, and I have like no interpretation for why the formula is like this. Just turns out to be like this.
Yeah, I'm sorry.
Exactly. Yeah.
Yeah,
So
yeah,
here I haven't written it, but I guess it was in the previous.
yeah, no, but I get it.
It's the length of the. It's the length of the.
Yeah.
So yeah, indeed, like before we were only able to compute like P1 and P2 equals like 2, 3, and 4.
Yeah.
But now it's nicer because we have really like the closed formula for arbitrary operators. And then as I was saying, like the caveat is that here there's some part that is not captured. But this part, fortunately, is just like a sum of two terms. So one corresponds to exchanging the tilt operator in the defect. The other corresponds to exchanging the displacement on the defect. You can figure out what's the correct symmetry factors, and then each of them is just like some hypergeometry. So somehow you have like a very nice formula combined with two reactors, and that captures like any correlator. So
Is the 3F2 the Mellin transformal defect block?
I mean, it's a Mellin transform of the Witten diagram. It's the Mellin transform of this Witten diagram.
Yes.
For delta 1 and.
But it is the same as the man transform of the defect conformal block.
No, they are different. I mean, so the usual story is that they are very much related. We have this. This is going to be a half and a half plus some sum over some coefficients. And then we have delta 1 plus
So I had are the box.
and then here you have some coefficients here. So it's true that the leading contribution is like this is supposed to be delta 1, delta 2. And so yeah, this is what people sometimes call a Polyakov relationship block.
Yeah.
And this is so it's almost the same that
Also on the previous slide, so what's the interpretation of sigma square term in the block?
I also have no idea. Like I was so confused initially. No idea. Something funny happening like in something happening for sigma square. Like
Is that the
it's
context? Should I
precisely-
interpret as a context?
it's precisely this it's precisely this tensor structure. I don't know if that tells you anything.
But this looks like a contact interaction.
Why a context?
Because
Yeah,
there's
exactly.
constant.
Because it's constant. Yeah, it's true. It's a content. Like, but remember that here you are also running over.
Yes.
Like you also have a sigma squared here.
Yes.
So it doesn't come along. I don't know. It's yeah. I wish I had it at the concept. Okay, but that's that's the result. Now I'm gonna give like some quick outlook, unless I want to talk more. Let me very quickly like make some last comments. So to summarize, we bootstrapped the tree-level contribution to this correlator between two chiral-primary operators in a Wilson line defect.
But tree level you mean leading order and supergravity.
Exactly, by tree level I mean like the first connected path. So we take the disconnected diagrams and then I don't know if it's standard terminology.
I mean the supergravity approximation is the lead. So
Yeah. It's a bit like for the 4-point functions usually like you would have like diagrams like this that you take out and then
Yeah.
usually people call tree level this. So it's like the analogy. Now the point of this bootstrap method is that it's very general. So in principle, it should apply to without changing almost anything. It should apply to Tooth lines or Wilson lines in other representations. So in principle, all we used is what type of operators appear in the effective action in IHES2. But in principle, these operators, the tilde and the displacement, you expect that they are going to be there like for any type of.
It's obvious that the bulk geometry corresponding to tooth lines is also not going to be backreacted. Like, you know, the
Here,
IHES2 is a probe brane.
Here I'm always assuming a probe brane.
So is it obvious that if I consider tooth line and n equals 4 super the dual will be described by a probe brane?
Yeah, it's very SQL to the D1 brane.
Yeah, it's not obvious to me, but I don't know. Ethan was mentioning it's some D1 brane.
It's a D1 brane just from SQL to the polynomial stream after D1 brane. It's on the same AES2.
Okay. And
You get the single D1 brane, that's the back rack. But the moment you consider top lines, which on the ADS side are engineered by many D1 branes, that call their N, you'll start the back rack.
But can I ask, like, what's the interpretation of back reaction in
It will change the geometry, like there'll be the
Yeah.
one step Tucker and the Gomez studied the bubbling geometry.
I understand, but then from the CFT, it's not a defect CFT anymore.
It is a
It is
defect
defect
CFT,
CFT. It's just the inner pole of feedback reacts on the the superconformal multiplet. So you have to reanalyze your equation, and what you find instead of ADS5 times 5 with the probe brane, instead you have a different geometry.
but boundary is still a defect CFT.
But if the geometry is not just like ADS5 or ADS.
But it has the same
like
isometry as a DCFT.
I see, so it doesn't matter, like it is the.
Yeah.
Asymptotically it's the same, I think. But
That's
it's
not
deep
the
in the
same.
bulk,
Yeah. But but it's not IDS5 MS5 anymore, but it has the same symmetry as the defects here.
Because the thing that confused me is that since the geometry is slightly different, then
You are allowed to make them different, right?
Yeah.
Because you're not preserving PSU 2,2/4 anymore, which is why it's P4/4.
I learned something. So anyway, so the point is that yeah, also like another comment, like yeah, you can also engineer like Wilson lines in other representations. So when I was talking about the fundamental representation, you can also consider. I think it's like something 3 days. I remember something mentioned where they consider this background. And then in principle, you can also consider surface defects n equals 4. You can consider like boundaries.
For boundaries, the bulk geometry is much more complicated than just having the probe.
Yeah. For boundary, there's no way to make approximation, but you can consider interface.
Interface, yes.
Then you have
I
a
think for
probe.
boundary, you will not be able to use the same technology.
Maybe boundaries not the same. But like I'm thinking maybe about
Interface,
if
I
we say
think.
like this defect branes intersect with
The interface.
Then of course there's other setups, right? Like one can, instead of considering equals 4, then one can consider, let's say, ABJM theory, which would be ABS4, or one can consider 62,0 theory, which would be ABS7. And then these theories, they also have like some defects. So after our inversion formula papers, some people already looked at the 62,0, but they only looked at the, let's say, like the 2-2 correlator, like the lowest lying one. So in principle, like this whole structure that appears to be there, like this whole simplicity of all the higher, let's say, like all the higher length operators, this hasn't really been explored for this sake of the defects. Yeah. And for HPPS with some lines, this whole setup also has not been explored. So it would be nice to see like similar structures also applying in other setups. And even better, like there's some papers without defects where they are able to interpolate like between different dimensions. So they find like some 3 levels of gravity amplitude, and then they can see that these interpolate between ABS7, ABS5, ABS4. They have like some parameter. It would be really cool if here we could have the same thing, which is like dimension and dimension. Maybe you have like the 3-level amplitude. Maybe it's like wishful thinking, but I don't know, who knows. It would be nice to. And then again, like the result is very simple for the 4-point function of chiral-primary operators without defects. This was explained by hidden conformal symmetry. What this means basically is that instead of considering the space-time distances, you consider space-time distances minus some distances that live in some sphere. Okay, so in this case would be ABS5 times 5. And then you define like this type of 10-dimensional distance. And then you take like your lowest lying correlator, let's say 2, 2, 2, 2, and then you consider it as a function of this funny x. And then the statement of this hidden conformal symmetry is that when you Taylor expand in y, you're going to generate like all these reduced correlators for one. So essentially, like the 2, 2, 2, 2 correlator contains all the information of the higher one.
Mainly, the distance in this 10D space should be xij square plus yij square.
Yeah, I don't know exactly why this minus, but I guess it's because the curvature, like, one has positive curvature, the other negative. I also never fully understood. But yeah, essentially the point is that it turns out that like all these correlators are generated by the 2, 2, 2 correlator. And intuitively, maybe this is kind of clear because you can imagine that this whole thing comes from 10-dimensional string theory, and then you are compactifying, and then when you compactify, you take like the supergraviton, you are generating like a bunch of Kaluza-Klein modes. All the correlators of these Kaluza-Klein modes, they have to be related to each other in some way. So it's clear that there has to be like some 10-dimensional structure hidden in these correlators. But I think the surprising fact was that it's actually so simple, and it seems to be related to some type of conformal thing. I think that's the part that people found really surprising. So here, I guess, I don't know, like just wishful thinking, but perhaps like if someone could uncover like similar structure, like by how do you explain, like, this nice formula that I was writing, like, can you understand it coming from 10 dimensions? It's a bit unclear to me whether it can be done or not, but it would be really nice if it's possible. So with this more, I don't know, ambitious type of future directions, I stop, and thanks for listening.
Just a quick comment about the enhanced symmetry. So actually, a case where this enhanced symmetry may appear naturally is for a line defect, but for the case of a line defect that correspond to a D3 brane, wrapping ADS2 contrast to inside ADS5. In that case, naturally you have this ADS5-2, which is very similar to ADS5-5.
Do they have the same radius? Because
They have the same
They
radius.
have the same radius, because apparently for what people have observed for point functions is that you always have this type of geometry, but sometimes like the ADS and the sphere, they have different radius.
Yes,
Then it's not conformally flat, and then they don't.
that's right.
This. Okay, but nice. So, what representation? Like,
It's a symmetric representation.
It's funny because I would imagine that probably this result.
And also the minus sign, I think, is related. I think you want to work in the embedding space.
Mhm.
And the minus sign shows up in the embedding space. You think about writing S and the sphere and the ADS in the embedding space.
Yeah, you probably interesting because here I would imagine that this correlator it should almost not change for symmetry.
Yeah. Yeah, I'm a bit confused about that. Because the interpretation is very different.
Yeah, interpretation is very different, but up to maybe some overall normalization, probably this.
But that would be magical, right? It's like the bulk object is totally different. Somehow, when you sum up all the Witten diagrams with totally different vertices, you get the same answer. Up to overall coefficient.
Yeah, that would be interesting to understand. I guess it boils down to asking whether in this ADS to effective action, whether there's going to be like more than just like field and displacement, or not. I guess if it comes from a D3 grade,
Yeah,
I could imagine that maybe
there are more fields.
there are more fields, so
Yeah.
perhaps some of them they contribute. So then maybe this answer that I'm using is it's missing.
Exactly. So there may be a different
So
solution.
maybe it's missing pieces. They restore these fields. Yeah, it would be nice to. Any other questions?
Can you extend this to higher points or
Yeah, so people for like I'm always talking about 4-point functions without defects, but people are already doing like 5-point functions. So people are already managing to do more than the simplest. So I would imagine that here it should also be possible. And not only possible, but maybe even easier than for like a 3-point function here should be easier than a 5-point function without defects. I would imagine. Or maybe like a 2-point function that putting some operator at the boundary of ADS2. Here you can slowly increase the complexity. Like for sure it should be possible.
And one other question is the continuation of these to Lorentzian straightforward or this week?
I would say it's but Lorentzian is always subtle, I guess, right? But I mean, like it has a clear interpretation. Like in Lorentzian, it would be like this type of picture I was drawing, where you like where you scatter something and then it comes out like some kind of process. And then I guess this would be time. So it does have like a clear interpretation. They wouldn't really want to do something. But I think, yeah, usually going to Lorentzian there's always that.
It's nicer maybe from Mellin and Mellin's space or something?
No, that doesn't change. I mean, yeah, like the claim usually is that the claim is that this type of functions you can actually like they are analytic in the translations. So in principle you can just the analytic structure is what I'm saying. So it doesn't really matter. So usually, yeah, I feel like I'm not explaining. Coming back to this picture I was showing before, basically the only thing that changes between Euclidean and Lorentzian signature is the interpretation of these closed ratios. So in Euclidean, we can think of this as some complex coordinates, like pi and e to the minus like, and then that's Euclidean. Where R and phi are actually unknown. But then in Lorentzian signature, you have the T and T bar, they are real and independent. So somehow, like the only thing that changes, like the amplitude is supposed to be like analytic up to branch cuts in both C and T bars separately. But the only thing that changes is that in Euclidean, you should look at this section where T and T bar are complex conjugate from each other. In Lorentzian, you should look at the section where the antiviral is. So you can imagine something like you have like something that lives in C2 to C2. Something that lives in C2, and you are asking like how you project it. But it's supposed to be like up to line.
Your question on the chat?
Yeah, again, yeah, I'm always considering SUN, but I would imagine that like this method is very general. So I don't know, like if you consider, yeah, what's going to change if you consider OL?
Yeah, what I'm thinking is, sorry, can everyone hear me?
Yeah, we can hear you.
Yes, okay, yeah, because what I'm thinking is if you want to produce ADS2 what volume, I'm guessing you have to make your, in string theory, you have to make your string like goes to infinity and to infinity, right? So that's like only the genuine inline defect can be, can has this property. Like in the SUN global structure, only the F1 string can add at infinity. So you have ADS2. The top line is kind of, the D1 string cannot add infinity because you don't have the correct boundary condition for the topological field theory or something like that. I guess this is more or less related to what Ethan like has comment on this top line and a D1 string. It's kind of tricky in this case, in the SUN case. But if you have SUN not ZN, then you can have D1 string add on infinity, then you might still have ADS2 in some sense, but you need to be careful whether you take the correct order of limit to have that thing, because D1 is kind of not, it's S2 over F1 string.
So you consider D1 for any measure and not VN. That's the
But at the end of the day, like, but it's like here it's just like my own. But at the end of the day, like all you need is to have a rough idea of how this effective action looks. And I think that's very generic. Like in holography, you always have like some ADS, and when you have a defect, you're gonna have a lower dimension ADS. How you get this from supergravity, that's gonna change like the details, whether it's any for in this UN or not. And with that, yeah, I'm definitely not an expert. Yeah, but I wish I knew more.
Yeah, I would say just the calculation is correct, just the interpretation will be different.
Exactly, like, and probably like some overall coefficient you're going to need to change. Maybe you need to add extra units.
So the line operator you choose to build this ADS2 is always the genuine inline operator in your equal for superamials, right? Like no matter what global structure I choose.
I mean, the comment is that I'm not even, since it's this type of bootstrap philosophy, I'm not even thinking too much about what operator I'm looking at. Like somehow, all I need is this effective action. I think maybe I'm not answering your question, but all I need is like to know this effective action and to have a way to fix the overall normalization. Okay, so then to get this effective action, it's true. I'm expanding a string also to get an idea of what it is. And then the next moment when I use the other moment where I use information about the string is here. So here, to get like this localization from DS2 to the Gimenez, here you're actually using n equals 4. You're using that you're considering like the Wilson loop in n equals 4. But actually, this type of localization, it works for any gauge group. So here, like at least this, you only need to change like how you take these traces. So if you're considering SUN, like you take these traces in a certain way, you want to consider SON or I don't know what you want to consider then. So I guess SUN mod C is not going to change anything, but I mean it's going to be.
Maybe just a comment to address Xinyan's question. Yeah. So the fact that this line being genuine or not is important, but it's not important for the observable that Aleix is talking about, because the other insertions apart from the line operator, whether it's genuine or not, are point operators, and they are transparent to this to the one-form symmetry generator that you were thinking about, because they are two-dimensional topological operators. So this observable does not depend on whether W is genuine or not.
Okay, so
but if you have another line operator inserted, that will be relevant. It just comes from the consequence of the point-like operators are never charged under one-form symmetry in 4 dimensions, because the codimension is too high. Any other questions? Well, if not, let's thank Aleix again.
I think I didn't understand the question initially. So he was asking more about like this thing that sometimes